So what is RAM? Well, RAM can be thought of in chemistry as an average. It's the relative atomic mass, and it represents an average mass for a given element. Now, you might be thinking, well, chemistry is meant to be an exact science. Why are we talking about averages? Surely elements have exact masses, and surely we can work that out somehow. Well, we need to think back to the idea of isotopes to answer that question. So the relative atomic mass, or RAM, is an average of all the isotopes in an element. So going back to that idea, we know that atoms can have different numbers of neutrons. That's one of the subatomic particles that give the atom mass. So if they have different numbers of neutrons, that gives them different masses. That means all the atoms in an element, even though they are of the same element, can have slightly different masses. Now that's really important, since most elements actually exist as a mixture of isotopes. They're not all the same, they don't all have the same number of neutrons. So that means some of an element's atoms have one mass, and some have a different mass. And usually there's 2 or 3, or sometimes even 4 main isotopes that you find in an element. So some will have this number of neutrons, some atoms, and some atoms will have a different number of neutrons. So what we want to think about then is the relative proportion of each isotope in a sample of an element, okay? Because that's always the same. So if I have a sample of a given element, I know, based on what element it is, and based on data that scientists have gathered, they will always have a relative proportion of isotopes in that sample. So essentially that means the mass of an average atom in a sample, if you like, can be calculated. The average atom in a sample of an element containing many atoms can be figured out, and that new average is called the relative atomic mass. And you can find all of the relative atomic masses for all of the elements on page 7 in the National 5 data book. So they're listed in this third column, all the elements are in alphabetical order, and then the relative atomic mass is given. So you'll notice that some of them are whole numbers, and some of them have decimal points, and we're going to explore in this video why that is. So, to take an example, I could ask a question like, what is the mass of chlorine? And when we think about it in terms of RAM, in terms of the relative atomic mass, this is a bit of a rubbish question. That doesn't really make much sense. What is the mass of chlorine? Well, what sample size are we talking about? What is the proportion of isotopes in a sample of chlorine? We don't really know. We don't really have enough information to answer this question. So that's not a very good question for a chemist. What would be a better question would be something like this. What is the RAM, or what is the relative atomic mass of chlorine, given that there are 2 known isotopes? And here they are. Chlorine 35, which makes up 75% of a sample of chlorine, and chlorine 37, which makes up the remaining 25% of a sample. So before we move on, chlorine 35 and chlorine 37, to write that in nuclide notation, just means that some atoms have a mass of 35 and some have a mass of 37. However, all chlorine atoms, because they are chlorine, have the same atomic number, which is 17, because they are of the same element. That never changes, remember, if it's the same element. We're only interested in the mass here, and that is another way of representing that outside of nuclide notation. We write the name of the element, and then the number, which is the mass number, after a wee dash, and that shows me which isotope I'm talking about. So chlorine 35 and chlorine 37 are my 2 isotopes in any sample of chlorine. And I know that 75% of any sample of chlorine of any total mass will be chlorine 35 atoms, and the other 25, the other quarter, will be chlorine 37, the heavier ones. So the question is then, what is the relative atomic mass? On average, what is the mass of chlorine in this sample? Okay, if I was just to pick up a random clump, how much of this am I going to get and how much of this am I going to get? And based on the fact that it's 75 and 25, what does that mean for my average? And how do I figure that out? Well, what we do is we take the mass of the first isotope and multiply it by the percentage of how much of that isotope there is. So in this case, our first mass is 35 and our first percentage is 75. And then I take that number and I add it on to the second mass times its percentage composition. So 37 times 25. And if I had more isotopes, I would just keep going, mass 3, mass 4, etc. And then when I've done all those numbers and added them all up, I divide the whole thing by 100. So to look at our chlorine example then, the relative atomic mass, which I'm interested in, of chlorine, would be 35 times 75, because I have a mass of 35 and there's 75% of it. And then I add on to that 37 times 25, the remaining 25% of which is made up of chlorine 37 isotopes. So I could figure them out individually, like so, and get a total number, and then divide by 100. Or if you have a scientific calculator, you can just whack this entire line into it and it'll give you the answer in a oneer. Just remember to include your brackets in the correct places so that it can do BIDMAS correctly. Then the final answer should be 35.5. And beside this, I'll just put a little u. For just now, that just means units, because here we could be talking about individual atoms, which would mean we were talking about atomic mass units, or we could be talking about moles, which I'll get to in a later video, in which case that would make this 35.5 grams. But for just now, what we need to know is that the relative atomic mass of a sample of chlorine, given these proportions of isotopes, would give us a relative atomic mass of 35.5. And maybe a way to visualize that would be to think of a number line. And on this number line, I've drawn the positions of the exact masses. So 35, 36, 37. Now ours is 35.5, which is about here on the number line. So why is that? Well, let's think about where our isotopes exist. So I have, if I just draw chunks of 25%, quarters if you like, most of my isotopes are on this part of the number line at 35, because there's 75% of my sample which has that mass, so most of them are over here. However, some of them are over here. So you can think of these little 25% boxes as having a sort of pulling power. So these guys here want to pull the average down this way, and this little chunk up here wants to pull the average back up the way towards 37. So if I start in between them exactly at 36, well, my average doesn't end up at 36, it actually ends up closer to this side because there are more isotopes over here than there are over here. So the 35 number has more pulling power, if you like. So I'm going to end up being pulled this way, exactly this much, exactly 35.5 in this direction, because there's that many in contrast to that many over here. So my average ends up being here on the number line. So you can think of it like that if that helps. But either way, always remember this handy formula here. So you take the mass of each isotope times by the percentage of how much that mass exists in the sample, add them all up, and divide by 100. And that will give you the relative atomic mass for a sample of an element, which is an average of all the isotopes in an element.